Good morning, or afternoon, or evening, since you could be watching this anytime, day or night. Some folks had indicated they were having some issues with this lab on finding reduction potentials, and I wanted to push out a quick video to discuss it and to maybe alleviate some of your concerns and confusion. So feel free to touch base. I'll try to do with a multitude of colors when I go through, and you can always reference timestamp and color if you have any questions. All right. So, the lab as a whole, basically we've got the various metals. He has 6, we had 5. They are the metal in a solution, just wet filter paper, of the ion. And then in the center is basically a salt bridge formed by some probably sodium nitrate or something along those lines. So what that does is that allows ions to flow through the filter paper just like they would through the solution or through the salt bridge, and that allows electrons to flow through the voltmeter. Now, one quick thing I want to point out, and that hopefully this isn't too small, is that if when we set this up, let's say we set up the classic 2 beakers with pieces of metal and all that, all right, and we have our salt bridge, then what's really going on is the electrons, what shall I say, the ions are flowing through the solution. So some kind of ions would be flowing this way, another kind of ions would be flowing that way, all right, in order to keep the solutions neutral. All right. Now, the thing I wanted to point out is that when you get into physics, for instance, you're going to say, but Mr. Ripien said we hooked a voltmeter up and it completed the series, completed the circuit, so that the electrons were flowing, say, this way, and the ions are flowing to keep the charge neutral, and there's a reaction happening in each container. Well, in reality, the voltmeter is actually, if you were to actually look into the box, it's not simply measuring the voltage as the electrons go through the wire. If you look at this purple wire coming in and out, it flows straight through. There's actually a parallel circuit that's set up that actually measures the voltage. So if next year you say, Mr. Ripien lied to us. No, I didn't. The voltmeter simply is set up in a different way. Alright, now, so what did we do? We hooked it up to the various things and we got voltage readings. That tells the strength of the various metals. So, in the first part, we were asked, where's my mouse? There it is. We were asked to find the reduction potentials and to compare the reduction potentials of the various metals. If you look at the various metals, who won? Who was victorious? Well, in this one, M3 defeated M1 and took its electrons. In the video he talks about the electromotive force. Well, in reality what he's saying is who's pulling on the electrons harder. So M3 pulled on the electrons harder than M1. But in all the other cases, M1 won. Sorry. Alright, so what was going on? So one of the metals is being reduced. So it's an ion, gains 2 electrons or whatever, becomes the metal. In the other one, the other metal, we'll call it Q, is losing its electron and becoming Q ion. Now, really important, I've seen some folks messing this up. If we have to double this to balance the reaction, for the oxidation we double it, it does not double the voltage. It does not change the voltage. Okay, the voltage stays the same. The push for a Q to lose its electron, or the pull for a Q to gain its electron, or the pull for a M to gain its electrons doesn't change because of the number of electrons being gained or lost. Okay, so who won? Well, I'll give you a few hints here. M3 should be at the bottom of your table because it had the highest reduction potential. Alright? Give you another hint. Who was next? Well, M1 beat everybody but M3, so M1 is going to be down here. Now, as for the other three, who lost the electrons most easily? Which one had the most force difference? So if we're looking at the voltage potential, the standard reduction potential between these two, or the voltage potential, which one was the weakest? Which one gave away its electrons most easily to, say in this case, M1? So who gave away its electrons really, really easily? Well, notice, in this case, we've got a potential of over 2 volts. That says the difference between the two was over 2 volts. So that says that M4 was ridiculously weak and gave its electrons away to M1 very easily. Okay, so what we've done is we've gone through and we've compared each of these to each other. I'm not going to fill in the other two. You can figure that out. So if M4 had a 2.02 difference from M1, and we're going to call M1 0, that says that M4 had a negative 2.02 voltage to reduce. Okay, let's make sure that makes sense, because we're saying, say blue is copper, then this we're saying had a 0 potential. So to go this way to oxidize, this had a positive 2.02 volts compared to copper. So if we reduce it, or if we reverse it and it reduces, that would have a negative 2.02 volt potential to reduce. Okay? Make sure if that doesn't make sense, you ask questions. Now, the predicted voltage. All you're doing is you're comparing the various things. So this one would have had a positive 0.48. So if in the case we were asked to compare M3 and M4 here, we would go, okay, who's going to win? M3. So M3's potential is 0.48 volts. Who's going to lose? M4. So M4 is going to be oxidizing, so it's going to have a positive 2.02 potential to oxidize. So the overall potential would be 2.50. We got 2.45. You know how to do percent error. Now, a lot of the questions were posed about data table 4, and quite a few people had some difficulty with this. So here's the deal. Copper is not really 0 on our chart. The entire chart is merely comparing the reduction potential of hydrogen, which we decided was 0. It's not really in 0 potential. It has a really high potential to react, but we decided it was 0. And so what, let me see here, hold on. Okay, so let me say it again. We decided hydrogen was 0. We made that up. It really has a potential, but we're comparing the potential of hydrogen to everybody else. So we called it 0, we set that as our standard, and compared everything else to it. Does that make sense? Well, you're not going to answer because I'm talking to a camera. Okay, now if we look at these, though, what we did was we had placed a solution of copper 2+, and it reacted with 2 electrons and became copper. And what we needed to do was we needed the actual potential for copper on a real chart. On our chart, copper was 0. So here's copper, copper's 0. Okay, we just said arbitrarily that copper had no reduction potential. But in reality, if we look on an SRP chart, standard reduction potential, it has a voltage. Okay, and if we look up copper, one of the things that is nice about copper, why we use copper in pipes and stuff, is it is more stable as the metal. It has a positive potential to reduce. Therefore, if we flip it, it has a very negative potential to oxidize. It doesn't react as easily as other metals. And so that's why we use it in piping and so forth. So the copper 2 plus potential is positive 0.34 volts. Well, all we're going to do is we're going to take our potentials that we found where copper was considered to be 0, and we're going to shift the chart. Okay, so if copper was considered to be 0 and metal 4 was considered to be negative 2.02 volts, now what we can say is, okay, in reality, copper is 0.34. Well, if we thought it was 0 and metal 3 was considered to be 0.48, if really the scale should be set up so that copper is 0.34, that means that metal 3 should be 0.34 plus 0.48. We're just going to slide the scale so that it actually lines up with the real chart. Because in the real chart we compared copper to hydrogen, and copper to hydrogen gave us an answer where copper was 0.34 volts. So we need to shift the entire chart. We need to shift our entire chart so that it matches up the real chart. So in this case, it's negative 2.02. Well, we need to change that by 0.34 volts. So it's negative 3.34 plus, or it's positive 0.34 plus negative 2.02. Looks like my pen's dying. Okay. So now what we can say is that metal 4 has a potential of, what is that? Do the higher level math. What? Negative 2.02 plus 0.34. 8 carry the 1, carry the thing. So 1.68. Is that right? Yeah. So we're saying that metal 4 has a potential of negative 1.68. Now, what we need to do then is we need to go into a chart and we need to go, okay, what is close to negative 1.68? What metal is close to negative 1.68 volts? Then you do the same for all the others. Okay? Hopefully that helps. Like I said, if you have questions, reference the timestamp or reference the color on the chart and let me know. This was a simple little lab. That's why there's no real data error analysis, nothing like that, because this would have been right before the AP exam normally, and so it was just a quick lab to make sure you understood the concept. All right. Hope everybody's doing well, and I will talk toward you, if not with you, at another time. Feel free to drop in on any of the sessions on Google Meets if you want. Take care.